So finally we get into runtime analysis. The surface analysis didn't tell us. It used a packer that we couldn't unpack. Stuff was still obfuscated. It has been the case where strings are obfuscated in a code like they're XOR'd, so that if you did a strings on it, you wouldn't see printable strings, but the code, in fact, is unpacked. And it may be the case if you don't know the obfuscation algorithm beyond packing, you go, I'm going to run this and see if I can determine what it's doing. That's what our mCarta system does, is to run it. So you need, and this is the analysis environment, this is the magic happens here, because you need to be able to do it in such a place where the code will act badly and find the resources it needs to act badly, like a DNS server, like a web server, like a DHS server, DHCP server, like internet access. Okay. And there's a program called HoneyD, H-O-N-E-Y-D, which is a Unix program that provides services. And so you run HoneyD in your malware analysis environment, and when it makes a DNS request, you've told HoneyD to answer DNS requests. When it makes a DHCP request, you hold HoneyD to do that. So there's a way to build your analysis environment with existing tools to do these kinds of things. So normally what happens in a runtime analysis, let's imagine you're building a runtime analysis out of VMware. You build your VMware Windows 7 analysis environment, you then snapshot it. Maybe you run a whole bunch of things in advance. So let's say you snapshot it. Then you put your piece of malware in there and you run that malware. Then you snapshot it again. Now I have two images of the system, before and after. I think there's tools called sysdiff. You can look at registry-mon. You can do a bunch of things to say, what did you change from this point? And get an idea of what that malware did in the process of doing its thing, if it acts badly. So that's where prepare the analysis environment. As I say, magic happens here. That's easy to say, challenging to do. Clear out the logs, execute it, do the monitoring, regmon, filemon, et cetera, to see what the tool does. Then if you got the information you need, filter out the normal changes. This is hard. Can you tell me what registry keys change normally when Windows runs? Anybody know? That's a hard problem to know. So this is another magic. Filter the normal activities means you know what those are, and I'm not sure we know. Then everything else is what the tool did. So you can determine through a runtime analysis what it's actually doing to the system. That seems to be easy. It can be summarized on one page. There's lots of steps. There's lots of things to do to get the right thing to happen. As I say, virtual environments, you can have multiple virtual environments. Here's Windows 7 Service Pack 0. Here's Windows 7 Service Pack 1. Here's Windows 7 64-bit Service Pack 0. So you can understand how very quickly the number of patches, the number of systems you have may grow very quickly for you to see how malware. And then, as I also said, it may be that the malware knows that it's running in a virtual environment, so it says, I'm not going to do anything bad. You can run me until the cows come home. I'm not going to exhibit any bad behavior, no matter what you run it under. Then it may be conditioned to IP address, or it may be conditioned to finding certain hardware, certain services. And you may end up having to do a reverse analysis just to make enough of the environment to make the malware act badly so that you can observe its behavior. So it's a challenge. You may have to provide native environments. You may have to have a bunch of disks and a way to take a disk image and splat it onto another disk and start all over again and have it run into native hardware. That takes a lot of time. It's easy to run a snapshot on VMware. It's hard to splat a 100 gig disk onto another 100 gig disk. That doesn't happen in a minute. That takes a lot of time. So think of all the 100 gig disks you've got with all the images of all the systems at all the levels that you need to test malware. So you can understand how this analysis environment becomes very complicated very quickly. So then you need some kind of a server that's passively listening, looking, for example, at all network traffic. Who is this communicating? It's trying to go to DNS. Let me answer DNS. Let me run network monitoring to see what's going on. Maybe I'm going to run Wireshark or a TCP dump or Snort, if you use Snort, to do network detection, and provide all these services in addition. And then I'm going to capture all the network traffic, and then I'm going to post-process it. So we have built this back at CERT. This is what the malware team does. There's a lot of stuff that goes on here. There's a lot of stuff just to make it work before you even analyze the first piece of malware. So the challenge of what has the malware done to the host? There's registry monitoring, there's file system monitoring, there's network monitoring. What all could it do from the host? And they need to see all those things to understand what it's doing. And I want to know that. We saw that run key, it's embedding itself so it restarts when the system starts. So now it's persistent. It speaks SMTP to somebody. What else does it do? What files is it opening? Is it in sort of hook in the keyboard? We already talked about credit cards. Maybe this web server was actually had a keyboard hook and it looked for 16 or 15 characters of numbers in a row and said, that's a credit card number, I'm going to keep it, I'm going to SMTP it up to my drop site, and nobody is the wiser. So anytime you type a credit card number in when you're purchasing something over the net at a holiday, those 16 characters, what follows 16 characters when you type in a credit card number? Expiration date, what does it look like?
And then 3 characters. 2 numbers / 2 numbers.
Month, day. Then what follows after that?
3 characters.
Yeah. So that's going to be what, 3 or 4 characters with CCV from the back of the credit card. So if I wrote a hook that listened to the keyboard buffer, if I find 16, boy, I'm going to start recording for a while. After a while, I'm going to stop when you stop typing because you've stopped entering all your credit card information. I'm going to put that in a packet. I'm going to obfuscate it in some fashion. I'm going to speak something up to some well-known server, and you're never going to know. And I don't care if you're speaking HTTPS to the web server. I've stolen it from the keyboard. So I don't care what controls you've done. I've now taken your credit card number. Okay, does that make sense? Relatively easy to do. And so it would be nice to know what that piece of malware is doing, who it's talking to. Hopefully you can find out who it's talking to so that you can do what? Get another warrant and go find out that system. And so what did the intruders do to make that, to render that essentially impossible? Flux. So they'll zip it to a host name. With fast flux, it'll change the IP address every 5 minutes. How do you write a warrant for that? The IP address at the time I requested this of the judge was this, and it's never been that since. So you're chasing your tail. That's what happens. And so this is hard to do, and once you find out the results, it's hard to know what to do next, is my point.
Will it be easier or harder with IPv6?
I assume everybody knows what IPv6 is, 128 byte IP addresses as opposed to 32.
Yeah. At home, I'll have more IPs than...
Right. Well, hopefully at home you have a 10 dot anyway, so you took a class A and non-routable. It's more data. I mean, fast flux. I've got more addresses I can switch it to. I don't think it's going to be easier. It may not be harder, but I don't think it's going to be easier.
Isn't like compiler an internal signature? So actually, by looking on an executable, you can kind of know CL like that it has an internal signature, and then you can know like, okay, that was downloaded from Microsoft website and that was something like that.
So you're saying that a compiler will identify itself in the compiled code?
I mean,
that's what I have understood.
That's also I think that actually is how compiler inside of compiler you have this, you can identify it by some signature kind of.
And my answer to that is we were working several years ago with people who were looking for specific patterns in files. And they were looking for files that had certain contents in them. Doesn't matter what the contents are. So they were running an automated tool. The automated tool looked for all the GIF files. Do you know what a GIF, how do you determine what a GIF file is? It essentially has a magic signature at the beginning of the file. I think it says GIF 87A at the beginning of the file. So I said to them, if I, as an intruder, went into that file and had it made it say GIF 87B instead of 87A, would you find it? And they said no. So I'm thinking that the bad people are going to take whatever the compiler puts in there and change it, simply so that your attempt to analyze it is rendered impossible. The really good intruders. I mean, the ones we deal with, the ones we catch are the ones who don't quite know everything. And the ones we don't catch are the more interesting ones, and they know how to make it so we can't catch them.